Next up, we have Anna Krelling, a software engineer currently working on ArcSlang project. Today, Anna will be speaking about ASTX, empowering language processing through custom abstract syntax trees. Anna will be discussing a versatile Python framework designed to build and manipulate abstract syntax trees. For those of you who don't know, ASTX is a fundamental part of compilers and interpreters, making it essential for code analysis, language processing, and transformation. Before I spill the tea, over to you, Anna. Thank you.
Hello, everyone. My name is Anna Krelling. I am a software engineer currently working for the ArcSlang project. And I would like to say that I'm very happy to be here at PyLadiesCon 2024. I would like to thank the PyLadiesCon committee for accepting our talk proposal. And today we're going to be talking a little bit about abstract syntax trees. So the title of my presentation is Empowering Language Processing Through Custom Abstract Syntax Trees. So since we're going to talk about abstract syntax trees, which I'm going to call ASTs for short, I'm going to give you just a little bit of context so you understand a little bit more why they're important, okay? So a little bit about compilers, interpreters, and transpilers. So they are all some sort of translators in some way, right? A compiler is a program that translates code written in one programming language into another language, typically turning high-level code into low-level machine code. Interpreters, they also translate code, but they do line by line instead of producing a full program in machine code. They're often used for scripts and or dynamic languages like Python. A transpiler is a little bit different. It's like a specialized compiler that translates code from one high-level language to another. So an example would be a transpiler converting from TypeScript into JavaScript. And as I mentioned, they are all some sort of translators. So what would be the phases of the translation process, right? So we have the front end, which is where the AST is built. So this is where the abstract syntax trees are built. So the abstract syntax trees are a tree-like structure of the code. And in order to build them, or the process to build them, it includes 3 steps in the front end. So a lexical analysis, which is where it's going to check your code and it's going to do the tokenization. So it's going to break the code in tiny pieces and it's going to check if each individual part of the expression makes sense. And then after that, we have the syntax analysis, which is also called parsing, which means that it will check if the tokens together make sense as an expression. And after that, you have the semantic analysis, which checks the code for remaining errors. And then after the front end, you have, or you may have, the middle end. It is optional. And in the middle end, optimizations can be applied to improve performance and efficiency, right? So in the middle end, DST is often converted into an intermediate representation, which is then optimized before being sent to the back end. Um, One example would be the LLVM IR. And then you have the backend, which takes either the AST or the intermediate representation, and then generates the target code, whether that's machine code for compilers or another high-level language for transpilers. So I already mentioned what are the phases of the translation, and I guess it could show a little bit why the ASTs are important, but let me try to emphasize it here, right? So in the front end, the AST is formed, it's built, and it represents the code's structure in a tree-like format. In the middle end, the AST can be transformed into an intermediate representation to allow for optimizations. And in the back end, the AST is used to generate the target code. So it acts as a bridge between the original source code and the final output. So now that I gave you a little bit of context and already told you why ASTs are important, let me introduce our project a little bit. So the ASTX um, is an agnostic framework for constructing and representing abstract syntax trees. So the X is because it's supposed to be language agnostic. So it's not made for a particular language. The primary objective is to provide a versatile and language-independent structure for ASTs with the flexibility to be utilized across various programming languages and parsing tools. Here you have an example of actually the image of our page, our web page, and also two links, one for the repo and the other one for the ArcSlang project. So I think the best way for me to show you what this project really is about is show you examples of what it can do, right? So I'm going to show you 3 examples. This is going to be the first one. This example is just import statements, right? So in Python, what we usually do is we import libraries, and sometimes we import libraries, but we want to call it something else, maybe because the name is too long or something like that. So here, the first thing that you can do um, is import the ASTX library. And then for the code to be represented in the AST, what do we do? Okay, so we want to import 2 different libraries. One is math, the other one is matplotlib, but we want to call matplotlib mtlb. So we create 2 aliases, one for each of the libraries that we want to import. And then we create the import statement, and then we create the AST representation, right? So here we have 2 AST representations. We have one with the purple background and one with the white background. The one with the purple background is the ASCII representation. So this is more for console environments. And the one at the bottom with the white background is it's a PNG representation, and it's more used in Jupyter Lab or Jupyter Notebooks, right? So in both of them, you have the nodes of the AST. So you have the import statement and the 2 aliases. So after we have, after I showed you those representations, now I'm going to show you something else that the ASTX library also does. So I mentioned briefly about transpilers. We also have a transpiler. So you have the 2 aliases and the import statement, and you can also have that translated into Python code, right? So now underneath the purple, the image with the purple background with the AST structure, you also have a code line in Python indicating what you meant, indicating the code that is represented by the AST. So I hope that with this quick example, it was clear that AST representation is something that we put a lot of effort into. So we want to make sure that it is as versatile as possible, that we have as many options as possible. So as of now, we have ASCII representation that is for use in a shell environment or in Python debugger environment. We have PNG representation, which is mostly used in Jupyter Notebooks. And we also have YAML and JSON representations that are very important for day-to-day activities and very often used as well. And then after that very simple example, now I'm going to show you something a little bit more complicated, a little bit more complex, which would be an example that involves mathematical expressions, right? So for this expression here, we're going to do this basic op. So what we're going to do is basically sum 1 plus 3 and then minus 2. That's all it is, right? So how do we do this? We import the ASTX library, and then we create the module, and we declare literals. It is literally the numbers 1, 2, and 3. And then we state the expression. So to state the expression, you can do that manually. And then you can also do that in a different way if you're working with parsers. So the ASTX project also has this versatility. you can do things in more than one way, right? So we have this basic operation of 1 plus 3 minus 2. And then after that, we append blocks. We append the block to the main module, and then we put this basic operation within the block, right? And then we go for the visualization. So you can see on the side of your screen with the white background. So we start with the module, and then we go for a block. And then within this block, you have a binary operation, a subtraction, right? And then you have an addition operation. So the addition operation is going to be between 1 and 3. And then the subtraction operation is going to be between the result of 1 plus 3 and the number 2. So this is what your AST would look like in a Jupyter Notebook environment. So those were somewhat simple examples. Now I'm going to show you something that requires a little bit more, right? So I'm going to talk a little bit about the Fibonacci sequence, which is a series of numbers where each number is the sum of the two preceding numbers. And this series usually starts with 0 and 1. So it typically looks like 0, 1, 1, 2, 3, 5, 8, and so on. So it's commonly used to illustrate concepts in programming, including recursion and loops. So let's demonstrate a Fibonacci sequence generator. Here, we're going to do an AST for that. So what we're going to use as a reference is this function, which is written in Python, which takes one integer as an argument. And the integer is actually the index of the Fibonacci sequence member, right? So if it's 0, it is the first member. If it's 1, it's the second member, and so on. So in this case, what do we have? If the if the input is either 0 or 1, this function returns the numbers 0 or 1 because the Fibonacci sequence starts with 0 and 1. But then, starting with the third member, so it would be as input, it would have the number 2. The return is actually the sum of the two previous members, right? So we have what we're going to call the base case for when n equals either 0 or 1, and we're going to have the recursive case for when n is different than that. So I'm not going to show you all the code to do the AST for this. The code is actually on this link, which is Jupyter Notebook, that shows all the code that was used. But I will walk you through the steps that were done for that. So first of all, you do a module, you initialize, right, the abstract syntax tree, and then you do a function. You include a function. You add a function. And within this function, you're going to have a block. And in this block, you're going to have a base case for when n equals either 0 or 1. And within this base case, you're going to have an if statement, as I said, if n equals 0 or 1. And then you're going to have a return block, and which is going to return the n itself. Besides the base case, we're going to have a recursive case in which we're going to have a binary operation. We're going to have an addition. And then this addition is going to be between two function calls. One function call of n minus 1 and the other one for n minus 2, right? So since we have n minus 1 and n minus 2, we're going to have also binary operations, subtractions within each of these function calls. So here on this next slide, yes. So here you can see the structure of the AST that resulted from all this code, or I guess all the code that follows this structure, right? So on top, you're going to have the module, and then you're going to have a function within this module. And then within this function, you're going to have a block that will have an if statement, which is for the base case when n is smaller or equal to 1. and then it's going to return the number, and then you're going to have, yes, you're going to have that return. If that's not the base case, if it's a recursive case, you're going to have your return is going to have a binary operation, which is an addition between two function calls. And the function calls are going to have a binary operation, a subtraction within them, because it's for n minus 1 and n minus 2. And then it's going to give the return. So here is what you would expect for the AST for this particular function. And that is it. I hope I was able to convey properly the versatility of this project. And I hope it was clear how much we're working on it, so it makes the life of developers and programmers easier as much as possible when dealing with ASTs. I would like to thank the Python Software Foundation, grants 2024. It was very helpful for us. Also the Open Science Labs, which is a very valuable partner, and the PyLadiesCon committee for accepting our talk again. Collaboration. So again, my name is Anna Krelling, and here's my GitHub page. Ivan is also working, Ivan Ogazawara from Open Science Labs is also working pretty hard on this project. And contributions are welcome. It's an open source project, so please feel free to go to our Discord page, join us there so you can discuss the project, and also go to our GitHub repo and check it out, see what you think, see if there are any issues that you can help with, test it out, see if there are any issues that you come up with. So thank you very much, and that was it that I had for today.
Now that was a deep dive. I hope you all enjoyed the session, and thanks a lot, Anna, for discussing all the compilers and interpreters. I, for one, really enjoyed it. Thank you.